one application of L'Hopital's rule is to compare how functions grow at infinity in relation to one another. So what do I mean by this? For instance, let's take a look at the graph of, say, the nth root of x. So n here is going to be a positive number. For concreteness sake, you can suppose it's equal to 2. So we're looking at the square root of x. And then I have natural log of x. So we might be wondering, well, what happens as we go out to infinity? We can wonder, will natural log of x wind up on top? Will square root of x always stay on top? How can we check these things? Like, which one is going to grow faster? So kind of the way I want to get a handle on this is just by taking a limit of one function on top of another. If that ratio goes to infinity, that's going to mean that the one on top is definitely going to grow faster than the one on the bottom, meaning the one on the bottom, when we divide by it, doesn't eat enough of the function on top to drive it back down to either a finite number or 0. Conversely, if I take the limit and I get 0, that's going to say that the thing on bottom grows faster because the thing on top, well, the thing on the bottom is just going to drive it down to 0 when we divide by it. Okay, that's just kind of fast and loose way of talking about it, but hopefully you can get the idea by looking at the pictures. So anyway, let's look at L'Hopital's rule in this case and see what comes out. I'm going to take the limit as x goes to infinity, natural log of x over x to the 1 over n. That's going to give me, when we take a look at our graphs, well, both of these are going to go off to infinity as we let x go to infinity. So L'Hopital's rule applies. Take the derivative of natural log of x, that gives me a 1 over x. Derivative of the bottom is going to be 1 over n times x, 1 over n minus 1. Okay, I won't clean that fraction up because it's going to clean itself up nicely in a second. If I want to clear the denominators here, I'm going to multiply top and bottom by nx. Nx times the top gives me an n. Nx times the bottom gets rid of the 1 over n. And we notice we're going to add a 1 to this, which is going to leave me with x to the 1 over n. Well, I have the graph of x to the 1 over n up here, and we see that that's going to go off to infinity, which means my limit here is going to go to 0. And that's because n here is a fixed number, so it's not going to have any effect on the limit. We could just pull it out. So we're really looking at 1 over x to the 1 over n. If you need something concrete, pretend that thing in the bottom is just square root of x. So it goes to 0. So x to the 1 over n is going to have faster growth than natural log of x. It's going to turn out natural log of x is sort of a slowpoke when it comes to growth at infinity. Let's take a look at the hierarchy and the pictures that go with it. So we have e to the x going to grow faster than x to the n, and being a positive number bigger than 1. Then we're going to have x to the 1 over n and a positive number bigger than 1. Then all the way at the bottom we have natural log of x. So the idea is going to be e to the x grows the fastest. If you take any number bigger than 1 and keep multiplying it by itself, it's going to grow about as fast as you can get in terms of the operations that we have here. Okay, x to the n is going to have the next best growth. You're just going to take a number, x, multiply it by itself. Okay, it won't grow nearly as fast as e to the x though. X to the 1 over n, well here we're taking roots, so roots won't grow nearly as fast as taking powers bigger than 1. And then, without knowing really what natural log is doing in terms of these algebraic operations in the middle, natural log just doesn't grow very quickly. And we see that on the graph. Okay, and here are graphs here comparing the 4. Okay, we could also just flip things over and then we'll have the same hierarchy, except instead of fastest growth, we'll have fastest decay as we go out to infinity. And so we see that same hierarchy, just the picture is going to be upside down. 1 over natural log of x is going to go out to 0 the slowest, so that's going to live on top. E to the minus x is going to go to 0 the fastest, so that's going to be on the bottom.